Okay, so this is the continuation of chapter 12. Remember, from Giancoli 6th edition. Remember, chapter 12 is about one specific kind of wave, which is sound waves. Okay, and remember, we talked in class very quickly about this slide. If you're interested in this topic on how we hear different noises, go and read your book, and I'm sure you can get even deeper explanations in your biology books. So, what is the idea of sound waves? Well, any vibrating object, any source of vibration can generate a sound wave. And human beings extended this idea and use this concept to create musical instruments. We have a variety of musical instruments. And this is what we'll be talking about now. How do they work? Well, the idea is, let's pick for example the drum. So in the drum, I hit that membrane. I have that membrane oscillating, vibrating. This creates regions of compression and expansions of the air around the drum, which goes on propagating and so creates this sound wave that will come all the way to my ear. Now, and a very important thing is that the oscillations of that membrane, the speed there is not the same as the speed of the sound wave. Now I have here two different media. One is the membrane and the other one is the air where the sound wave propagates. So two different media, the speed is completely different. But what is equal? The frequency. The frequency of the vibrations of the membrane is equal to the frequency of this sound wave that will hit my ear, and that frequency will give me the sensation of that specific sound. Let's pick another example. Let's pick the strings of a guitar. In the piano also we have strings, right? In the piano we hit the key, and this is a little hammer that hits the string and puts this string in this vibration mode, right? Creates in this string a standing wave, those standing waves that we talked about on chapter 11. So creates this standing wave on the string. This standing wave will then make the air around compress and expand, and that will generate the sound wave that will get to my ear. Okay, so here is clear again that the speed in the string of that standing wave is very different from the speed in the air. The speed on the string depends on what? Depends on the tension, depends on the density of that string. The speed in the air depends on the temperature in the air. All right? So two different speeds because we have two different media. What is the same? The frequency. The frequency of that standing wave on the string is the same frequency of the sound wave that will get to my ear and will give me the sensation of that particular sound for that particular frequency. Okay? The only exception to this story of speeds of the musical instrument, of the vibrations in the musical instrument, and speed of the sound is those wind instruments, those instruments where we blow, like the flute. And what do I mean by being an exception? In this particular case, the speed of the standing waves in the flute is the same speed of the sound wave that will come to my ear. Why? Because in the flute, the medium is air. When we blow the flute, we make the air inside the flute create a standing wave. Okay, so this is air also. So then in this case, I have the same medium of the standing wave inside the flute and of the sound wave that comes to my ear. This is the only case where the speeds coincide. Okay, but the frequency always coincides. So what we are going to do now is we are going to explore a little bit more these different musical instruments, which is a beautiful thing. If you have learned music, I think this topics will mean even more to you. So we are going to start with the strings of the guitar, the strings of the piano. And this is very similar to what we already saw in the end of chapter 11. What we have here, well, the string is fixed at the edges. No? So at the edges I have nodes. We are going to hit this string and create standing waves. So the lowest frequency, the one that we call fundamental of first harmonic, gives us this standing wave here, right, that goes up and down, seems not to be moving to the right, it seems just to be moving up and down, right? So creates this standing wave. And in this particular case of the first harmonic, I see that this whole length of the string gives me half of a wavelength. So this is what we are writing here. So the whole length of the string gave us half of a wavelength. Let me hit the string a little faster, give it a higher frequency, a frequency that is now twice the first harmonic. So we call this one the second harmonic or first overtone. And what we see now is that my standing wave has now the shape of a whole wavelength. So I have now L is equal to the whole wavelength. Remember that this little index here, 1, is to tell me that I'm talking about first harmonic. These are the index, I'm talking about second harmonic, and so on. Hit the string even faster, and now I get whole wavelength and half. So that's what we wrote here, 3/2 of the wavelength, right? So in this case, I don't have any node in between for the first harmonic. Second harmonic, I have just one node in between. Third harmonic, 2 nodes in between, and I can go increasing these frequencies. We already did this. We found a general expression for the wavelength. Now, by looking at each one of these cases, and you can even continue extending, what we concluded was that, well, how do I get this different wavelength as I increase the frequency? Well, it looks like I'm multiplying a natural number by half of the wavelength, and I'm putting this index here to remind me that I'm talking 1, 2, 3, and so on, right? This is what I'm seeing everywhere. In this first case, when n is 1, I get half of wavelength. In this second case, where n is 2, and 2 divided by 2 gives me the whole wavelength, and so on. So with this, just by studying all these cases, I was able to get a general expression, which I can then write this general expression for the wavelength. Twice the size of the string divided by n, where this n is any natural number, 1, 2, 3, 4, 5, whatever you want. Okay, now the speed in the string depends only on what you see here, depends on the tension and depends on the density. If I don't change the string, if I don't change the density, the speed is constant. So the speed is constant. I can then write an equation for the frequency. Since we know that the wave velocity is equal to the frequency multiplied by the wavelength, I can then write an expression for the frequency, which will be equal to v, the wave velocity, divided by the wavelength. So divided by the wavelength is 2L and n on top. Okay? So the standing waves that we can have on the string have this wavelength and have this frequency. Very nice. Now, there are some details about the strings of the guitars and of the piano that you may have notes. So one of them is the following. You may have notes, and if you play the guitar, you do it yourself. So let's try to make a drawing, very bad drawing here of a guitar, right? So you may have notes, folks. So let's pick a string here, one of the strings of the guitar. What the musicians do, they sometimes put their finger at a point of the string. So what are they trying to do when they do that? Well, you see that now, when they put their finger here, the string, instead of having this whole length, has now a shorter length. What does that mean? Let's look at the equation for the frequency. Let's write this equation here. The frequency is equal to V divided by 2L. Well, and the frequency N is N multiplied. Oh, this is not very nice. Let's write this again. The frequency of the harmonic N is equal to NV divided by 2L. All right. If I decrease L, what happens to the frequency? Smaller L gives me a higher frequency. So that's what the musicians are doing. If they decrease L, we get a higher frequency. So that's very smart. All right, so that's by putting the fingers at different positions, they get different frequencies. There is another interesting thing about the guitar. And what is that? Well, it doesn't have just one string. It has several strings. And these strings are different. Some of these strings are very thin. Some others are very thick. What do we gain by doing that? Let's think a little bit. So we have some strings that are very thin, some strings that are very thick, and some intermediate ones. Let's look again at the expression for the speed in the string, the speed in the medium. What does it depend on? You can see in the equation, well, that speed depends on the tension, fine, and depends on the density, on the mass divided by L. So, if this density increases, what happens to V? V will decrease. Okay, so let's write this down. Density increases, then V decreases. Okay, so as I change from this thin string to this thick one, what I do is I decrease the speed. And then what happens to the frequency? Let's write the equation for the frequency again. The frequency for a certain harmonic is NV divided by 2L. If I decreased V, that means I increase the frequency. Oh, sorry. Oh, if I decrease V, you see V showing up here, that means I decreased the frequency. So I get this lower sound, which you know is typical of very thick strings. Okay, so very interesting things that we can play with by changing the length, by changing the thickness. All right, let's move on and try to solve some problems. We talked about the guitar. Let's think a little bit about the piano. In the piano, nobody goes and put their fingers on the strings, right? Well, we have all those hammers touching those strings. But if you have ever opened a piano, you have seen that the strings have different lengths. Okay, so instead of putting our fingers, we have strings of different lengths, and some are very long. Okay, also in the piano, if you look at these different strings, you see that some are thicker than others. All right, thicker ones give us a lower frequency. Okay, now suppose I wanted to build a piano without playing with these densities. Okay, I wanted to have all of the strings with the same thickness. Let's see, would this be a clever idea or not? So this is what this first problem is about. What this problem is telling us, let's read it. They say, look, the highest key on a piano, so the highest meaning the one with the highest frequency. So let's write this here. The highest frequency is 150 times the lowest key. Okay, so the highest one is 150 the lowest. Okay, if the string of the highest note is 5 centimeters long, okay, so the length of the highest one is 0.05 meters. The question is, how long would the string for the lowest note have to be if it had the same mass per unit length? Okay, so the question is, what should be the length for the lowest one if I want to keep the same density? If I don't want to play with different strings, I just want to keep the same density, I will just play with the length. So how long would be this string that has low frequency? All right, Okay, so we are here talking about first harmonics, okay, about the fundamental. So the equation, if you remember the equation, let's look at that equation again. Yeah? So the equation for the frequency is this one. Let's copy it here. Yeah? So the frequency is V divided by 2L, and we are thinking just about the first harmonic. Okay, so N here is 1. Okay, so this is the equation we are playing with. Let's go back to the problem. So I wrote here, the frequency of the high is 150, the frequency of the low, and I can also use this equation here. So let's do that. Frequency of the highest is V divided by 2 length of the highest. Okay, and this is equal to 150, and the frequency of the lowest, I'm going to use this equation here, is V divided by 2 length of the lowest. You see the speed is the same because I'm not changing the density. The speed is the same, so I can even cross out these V's, I can cross out this L, and from here I'm going to get what we are after, which is what is the length that this low key would have to have. And you get to a huge number. If you make this length, if you make this low key of the same density of the high key, you would need to have a length 150 times bigger than this low one, which means you would have to have um, a string that would be 7.5 meters. Imagine a piano with this size. It would be a huge thing, would not enter in nobody's house, right? So that's why we then play with the density. Okay, so this is a very nice example of the importance of playing with the size, the length, and also with the density of these different strings. Let's go for the next problem. So in the next problem now, what we have is a violin. So we think about the string of a violin, and the length of this string is 0.32. So let's already write this down. The length is 0.32 meters. Very well. And we want its tune to play A above, middle C. Well, this is important just for musicians, right? What we want to do is play this frequency here, 440 hertz. Okay, so this is the frequency, the fundamental, 440 hertz. And now comes the question. First question is, what is the wavelength of this fundamental string vibration? Okay, so what is the wavelength for the string? So wavelength for the string. And let's see part B. Part B is, what is the wavelength of the sound wave? Okay, so what is the wavelength of the sound wave? Okay, remember what we said. The frequency of the string, of the standing wave on the string, and the frequency of the sound wave, they are the same, but not the speed, because I have here two different medium. If the speed changes, then it's natural to have two different wavelengths. The wavelength for the string, the wavelength for the sound wave. All right, so how are we going to get the wavelength for the string? So let's start here with part A. Okay, I'm going to use the expression for sound, for wave velocity, right? Which is wavelength multiplied by frequency. All right. Can I get part A with that? I could, if they had given me the tension, if they had given me the density, right? Because then I could compute this speed and from there get the wavelength. But they didn't give me that. So I have to go to another expression. What other expression do we have? Well, let's see. We are talking about fundamental. So if we come back to our drawing here, what is the fundamental? The fundamental is the one where the wavelength is 2L, no? When I'm talking about N being 1. So this is easier than what we started writing here. I can just say, the wavelength for this fundamental is just 2L. And since you told me that L is 0.32, so I know that this wavelength is 0.64 meters, or if you want to write as in centimeters, there you are. Okay, good. So we are done with part A. They didn't give me tension, density, or so on, but I could get the wavelength from the expression that I have for the fundamental. Let's move now for part B, the wavelength for the sound wave. And now I'm going to go really for the expression of the wave velocity. And let's see if I can use this one this time. Well, the frequency I have. And do I have the speed? Yes. Well, they didn't write this explicitly, but I'm telling you, we are talking about sound wave in the air, and we assume that the temperature is 20 Celsius. Okay, this should all be written explicitly, so I'm telling you this, which means that the speed is 343 meters per second. That's the speed of sound in the air at 20 degrees. So I can use this expression to get my wavelength. And if you come, the question is giving us 0.78 meters, which is 78 centimeters. Then comes the final question. Why is there a difference? Why do I have these two different wavelengths? Because we have two different media. The media for the standing wave is the string. The medium for the standing wave is the string. The medium for the sound wave, where the sound wave is propagating, is air. So I have two different speeds, and then I get two different wavelengths. The frequencies are the same, but the speeds are different, so the wavelength change. All right, so this is enough for the strings that we find in guitars, that we find in pianos. Let's go for another musical instrument. Let's think of those wind instruments like the flute. Okay, so now let's see one more case, a different musical instrument, and now we are thinking about the flute or a clarinet, no, those wind instruments. So what happens there? In the flute, there are two holes. There may be, but there are others that I use, but there are two very important holes. One hole is where I put my mouth, and there I blow air inside. So this is this point here in the drawing. This is where I blow the air. And what happens to the air that I'm blowing? It moves right and left, right and left. No? So the molecules there are moving right and left. And there is another hole at the other edge of the flute, which is indicated here. No, so this is a hole that communicates with the air outside the flute. And here again, I have the molecules moving right and left, making the air around the flute vibrate, no? And create the sound wave that will come to my ear. Okay, so you see this is a little now different from the string. In the string, at the two edges, we had nodes. So there was no motion of the string there. Here in the flute, at the two edges, we have antinodes. We have motion there of these molecules, these air molecules. Okay, and as a result, we get this different graphical representation. Remember, let's have a look again at the case of the string. No? So I have these two nodes, so no motion at all at these edges, and the graphical representation then had 0 here, and the extremes showing up in the middle. Now for the flute, here I have antinodes. Now I have antinodes, and these lines that you see here are graphical representations of this motion. Now, so this is a little different from the string. The graphical representation of the standing wave in the string also coincides with the motion of the particles. Here, no, the motion, the real motion of the particles are here, right and left, right and left. This line is just representing the amplitude of this motion. So it's really an abstract thing. Now it's just a graphical representation of the actual motion of the molecules. Okay, so there are these differences from the string. Also, the medium is different. No? In the string, we have the string, so it depends on the tension, depends on the density. Here, the medium is just air. So the medium within the flute is the same medium of the propagation of the wave sound. All right, but despite these differences, we end up with very similar equations. So let's come. This case here is the fundamental. Now, so I have antinodes at the edges and I have one node in between. So this is the lowest frequency. And what do we get there? Well, if I look at this is the whole length of the flute. And what I get, I can see from this graphical representation, is again half of a wavelength. Now I go from um, crest here to trough and I don't go back. So it's half of a wavelength. So it's the same thing that we had before for the string. It's a little different what is happening here. The shape of this standing wave is a little different, but we again get the same um, equation for the first harmonic for the fundamental. Increase the frequency. What happens? I get one more note and I get one more note in between the edges of the flute. And now what do I have? Well, crest, trough, back to crest. Well, this is a whole wavelength. So the length of my flute is now giving me a whole wavelength. Increase again the frequency. Get one more note. So I have 1, 2, 3 nodes in between. So I have crest, trough, crest. This is whole thing is one wavelength plus half. And so 1 plus half give me 3 halves. So you see, I recovered exactly the same equations that we had for the string. No? By playing with all of these different harmonics, I can get this general equation that the length is equal to n being a natural number, lambda divided by 2, and this is just the index. So now I can write lambda as 2L divided by n, since the speed of the inside of the standing wave I know, it's constant because the medium is just 1. So I can also get the frequency using the expression for the wavelength. So the frequency is the speed divided by the wavelength. So exactly the same expression that we had for the string, but you see that the motion is different. We have now these longitudinal waves, and at the edges we have antinodes instead of nodes as we saw for the string. Okay, let's go for one last musical instrument, which is very particular, and this is the case where we get closed tubes. This shows up in organs. In organs, if you go and have a look, there are different kinds of tubes. There are open tubes, just like the flute that we saw with antinodes at both edges, but there are also closed tubes. So these closed tubes, they work like this. There is one point where the one edge which is open, where the air is free to move right, left, but there is another edge which is closed. There is no hole there. Okay, and as a result, in this case, we do get different equations from the other musical instruments. So let's see what we get. So this is the whole length of the tube in this organ, and since this is antinode and this is node, we don't even get half of a wavelength anymore. I go crest and middle point. I don't even get a trough. So now I have here that with this whole length, I get 1/4 of the wavelength. Okay, so the first harmonic is 1/4 of the wavelength. If we increase the frequency, then we finally get one node in between. But with this node, what do we have? Look, from here to have, I have half of a wavelength, half plus 1/4. 1/2 plus 1/4 gives us 3/4. So this next frequency here gives us 3/4 of the wavelength. Since it's 3, now this is called third harmonic. So we skipped the second harmonic. There are no even numbers showing up here. We go from 1/4 to 3/4. Okay, increase the frequency. Okay, one more note, and now what we have from here, now crest, draw, crest, I have a whole wavelength, and then from this point to the edge, a quarter. So 1 plus 1/4 gives us 5/4. And since it's 5, this is known as fifth harmonic. Now, so we have the fundamental and the other overtones, but we go on skipping the even harmonics. Now we have here in the numerator only odd numbers. So my general equation is a little different. See, the general equation is L, the length of the tube, is equal to N, where this N is only odd numbers, 1, 3, 5, 7, 9, and so on, multiplied by the wavelength. We put the little index there to indicate which harmonic we are dealing, divided by 4. Okay, so this equation is different from all the other musical instruments that we saw. Again, using the wavelength, using the wave velocity, we can then write an equation for the frequency. No? So from this top, I see that the wavelength is equal to 4L divided by N. Remember, this N is just odd. Using the wave velocity, we can then find that the frequency is the velocity showing up here divided by the wavelength. The wavelength is 4L divided by N, so the N goes into the numerator. So this N here is just odd numbers, 1, 3, 5, 7, 9, and so on. So very particular kind of instrument. And let's then finish now with some problems. We are just going to solve these first two problems, okay? Forget about this last one. Each person does a different estimate, so we get different numbers, so it's not so important. Let's focus on these two first problems, 12.9 and 12.10. So let's read 12.9. They want to know the fundamental frequency and the first three overtones. The first three overtones. So they want to know the fundamental F1 and the other overtones, the ones above the fundamental, for an organ pipe. Okay, so remember organ pipes, they have closed and open tubes. For an organ pipe that has this length, 26 centimeters, it's at this temperature, 20 Celsius, which means that the speed of the wavelength in the air, the speed is 343 meters per second, and we want to know these frequencies in the case where the tube is open and in the case where the tube is closed. All right, so let's go and try to solve this problem. We saw already the equation, so let's write them down. In the case where the tube is open, so let's write here, in the case where the tube is open, we saw that the frequency is equal to N, and then we have the speed, the wavelength velocity, divided by 2L. Okay, this is the case as in the flute, where both edges are open. In the case of a closed tube, where just one side is open but the other one is closed, is that very particular case. What we saw there is the frequency is NV divided by 4L, and careful, this N can only be odd. Okay, so this is it. We just now have to put numbers into this equation. So since they gave us the temperature, what they are giving us is V, right? It's saying that V is 343 meters per second. And the length they also gave us is 0.26 meters. And from there you can get the frequencies. In the open case, we'll have the fundamental F1, and then they want the next three overtones, so F2, F3, and F4. In the case of the closed tube, we'll have the first, the fundamental F1, and then, just careful, we'll have F3, F5, and F7. And that's it. So it's not a hard problem. Let's move to the next one. In the next problem, what do we have? A flute designed to play this frequency, okay, and they are giving us this frequency, 262 hertz, and this is the fundamental. So let me put F1 here. This is a flute, so I know which kind of equation I have to use. Now it's the equation for open tubes. And what else they tell us? They want to know how long this flute should be, the distance between the mouth and the other edge of the flute. So what is this length? And we are assuming here that we are at 20 degrees Celsius, so the wavelength, the wave velocity is 343 meters per second. Again, it's just a matter of putting things into the equation. Which equation? This one. The frequency is n is 1, v divided by 2L. So we have the frequency, we have v, we get 2L. So that's it. Again, not a hard problem to solve.